Alrighty, so we will continue our course in statics by introducing the first real bit of statics we need to know. First of all, statics, of course, implies that things are not moving. Things are stationary. That, of course, is as opposed to dynamics, which is a system is in motion. So in general, as we progress through the course and we work on statics, we're going to be assuming that whatever system is being worked on, that system is not in motion. It's a stationary, static system. Now, why is this important? Well, it's important because the big equation, actually set of equations we're going to be using in this class is basically F equals ma. The sum of the forces acting on a system equals mass times acceleration. Now, that's Newton's second law in physics, of course. And this implies for statics, if the object is not in motion, then certainly it has no acceleration. And thus, the sum of the forces acting on a system is equal to 0. So if you're given a statics problem, you'll know it's a statics problem either because explicitly it says the object is not in motion, the object is in equilibrium, things like this. And what that implies, the thing you need to understand about it is that means that if you add up all the forces which act on the system, it equals 0. Now, for the first part, this chapter 2 we're working on, which is basically how to add vectors, it's forces acting on the system. We're going to have examples where the sum of the forces is not necessarily equal to 0. There may be a net force. But this is just to get us used to the method of solving problems. Once this chapter is over, pretty much all of the problems we will work on will have the sum of the forces equal to 0. Now, I said there's a set of equations we need. First of all, understand that what this means, the sum of the forces, that means in the x direction, the y direction, or the z direction, because this is three-dimensional. And as we talked about when we talked about vectors, when you work on an equation, if it's a vector equation, we already know we cannot add vectors together unless they're in the same direction. The implication of this is that every equation you write down must be in one of these three directions. So you'll actually have the sum of the forces in x, the sum of the forces in y, and the sum of the forces in z, all separate. You cannot mix x, y, and z direction stuff together in one equation. So when I write down the sum of the forces is equal to 0, or the sum of the forces is equal to ma, that's really three equations. The sum of the forces in x equals 0, the sum of the forces in y equals 0, and so forth. But for now, I'm just going to count Newton's second law, this F equals ma thing, as one equation, even though we know deep down it stands for 3. There's another equation we need for this course. And that equation is the sum of what's called the moments. And that's equal to I times alpha. In physics, moment has a different term, and it's called torque. So in physics, we learn about torque. That's basically the force which gives rise to a rotation. And what that means is you have like a wrench on a bolt. You apply a force to the wrench to try to turn this bolt. Well, you calculate because of this force and the distance from the bolt to where the force is applied, call it R, the torque is R times F. And we did that in general physics. In engineering, for whatever reason, engineers have a different word for torque, and they call it moment. So in this course, when we talk about torque, we're going to be calling it moment, capital M. And so just like, as is true for forces, the same is true for moments. If a system is not in motion, that is, if a system is in equilibrium, then not only must all the forces be equal to 0, but also all the moments. Because if the moments don't sum to 0, then the object must be rotating. And if an object's rotating, obviously it's moving. So the other static equation we're going to have is the sum of the moments is equal to 0. Okay? So in this class, sum of the forces equal to 0, sum of the moments is equal to 0 will be every equation we will have to use, which is really nice. No more whole page formula sheets or anything like that. All we have are 2 equations. Now, the next thing we need to know is for this chapter, basically what we're going to have are systems, let's say a stake or a bar or a wrench or something, and on that system are applied forces. Okay, so there's going to be a set of forces acting on a system, and we're either going to say what's the sum of the forces, find the resultant force due to these separate forces, so what's the total force acting on the system. Or we're going to say something like, in order for the total force to be purely horizontal, what must be F1 if you know F2? Okay, so basically for this chapter, we're going to have a system. The system has a bunch of forces acting on it, and we're going to try to add the forces together to get a resultant force. Sometimes we want to know what is the resultant force. Sometimes we're given the resultant force and we want to know what one of the individual forces is. So there's different ways of asking these questions, but at the end of the day, we're using F equals ma. The big key here, obviously, we did this in General Physics 1. This is after you do kinematics, you go to Newton's laws, and the F equals ma, that's Newton's laws. So we've done this before in physics. However, what we're going to find is here in engineering, in a statics course, some of the questions are not quite as straightforward, or even if they are, there may be sort of faster ways of solving the problem. And so what you're going to see is that physicists and engineers don't always solve the same problem in the same way. There's 2 different methods. And I'm going to try to show you both methods. And in fact, what I'm going to do is I'm going to split this topic up into 2 different videos. One, solving it the way physicists solve, which is called the component method. And the second one, which a lot of times engineers will use, is called the triangle rule. Now, both of these methods are solving the same thing, F equals ma. But the reason they're different is because F equals ma being a vector equation, these forces acting on the system are vectors. So in order to add the forces together, we have to know how to be able to add vectors which are in different directions together. In physics, we learned the component method. That is to say, for every vector in our problem, break each vector up into x and y components. Then you can add all the x component stuff together to get a total x, and add all the y component stuff to get a total y. And once you have those 2 things, you can combine them together to get the magnitude and the direction. The triangle rule is trying to do the same thing, but instead of using right triangle trigonometry, they can have a more general triangle, but because a general triangle is not a right triangle, they can't use SOHCAHTOA stuff. They can't use sines and cosines anymore the way we do in physics. So they use a law of sines and a law of cosines. Sometimes it's faster to do it this way, sometimes it's not. For the most part, I'm going to allow you to choose which way you want to solve the problem. Only a couple of times am I going to mandate solve it this way versus this way. So if on a test, for instance, I want you to solve it using the triangle rule, just to show that you understand how to do it, I will be explicit about it. If I'm not explicit about which method to use, you could use either method. I found in general people use the component method because you've already taken physics, so you're used to that already. However, if you want to get used to triangle rule stuff, or you, for whatever reason, you kind of connect with it a little better, feel free to use that method too. At the end, our answers will be very similar. They won't be perfect, because what I've found is rounding errors are slightly different between the two methods. So one answer might be 2.53, another answer might be 2.61. They're very close, but they're not exactly the same. But they're close enough. All right, so for this video, we are doing component method. And what the component method says is, given a system of vectors, break each vector into its components. Now what that means, it could be x and y, or it could be parallel and perpendicular. I'm not being very specific that it has to be x and y components, because you may be given a problem where the bar is angled at some weird angle, and then you have these vectors acting on this angled thing. Sometimes it's not necessarily easy to make it x and y stuff. Sometimes you may want to make the coordinate system parallel and perpendicular to the bar. So, but at the end of the day, you're always going to be breaking into components. It's just up to you what your axes are going to be. Is it going to be x and y components or something else? Once you've broken all the vectors up into components, add components piecewise, which basically means add x's with x's and y's with y's. And that'll give you some final resultant, x, and some final resultant, y. And then calculate magnitude and direction. Okay. And basically, if you remember, magnitude was square root of the x component squared plus the y component squared, and direction was inverse tangent of the y over the x. And obviously, if you're not doing x and y, but you're doing parallel and perpendicular, x is the same as parallel, y is the same as perpendicular. It's just variable names. All right, so same rule from general physics, nothing new here. So let's go ahead and do an example. So here's an example. Let's say I have some kind of a bolt or a screw, one of these kind of hook type screws that screws into the ground. And on it, I've got 2 ropes and maybe it's a little screw. This rope here I'm pulling on with some force F1. Let's say that's 100 newtons. And let's say the angle, this angle here, let me make it a little more clear that it's angled. Okay, there's your bolt. So here's the first. Here's the second rope. F1 is 100. And it makes an angle with the horizontal of, let's say, 15 degrees. And an F2, this rope I'm pulling on with a force F2 of 150 newtons. And let's say this guy makes an angle with the vertical axis of 10 degrees. For this example, I want to determine the magnitude and direction of the net force. Okay. So again, I've got this kind of hook screw that's been screwed into the ground, and then there's 2 ropes coming off of the hook being pulled on. That is to say, in engineering terms, they're being tensioned. So there's a tension in rope 1, call it F1, of 100 newtons, angled at 15 degrees above the horizontal. And there's a second rope whose tension is 150 newtons, and he's angled 10 degrees to the right of the vertical. And I want to know, given these 2 forces, these 2 tensions acting on the screw, what does the screw feel? What's the total force he feels, and in which direction is that force being felt? Another way of saying this is, if I wanted to remove those 2 ropes and just put 1 rope, such that the screw feels exactly the same thing, how should I pull on that 1 rope, and in which direction should I pull so it's the same? Okay? That means the same thing. All right, well, as I said, we're using component method for this video. Next video, I'll do the same problem, but with the triangle rule. And so what does the component method say? First step is break everything into x and y components. So let's look at F1. F1, I need an x piece and a y piece. Okay. I'm going to draw it here and then erase it just so I have some room. Here's F1. Here's the horizontal. Here's the vertical. I know this is 15 degrees here, and I know this is 100 newtons. What I want is x and y. Right? There's my right triangle. I want the side x and I want the side y. Well, obviously, the x side is the side which is adjacent to the angle. And we remember from SOHCAHTOA, adjacent goes with cosine. So the x component of this vector is 100 cosine 15. We'll get out our calculator, calculate 100 times the cosine of 15, and we get 96.6 newtons. So there's my x component. What about the y component? Well, the y side is the side opposite to the angle. Opposite goes with sine from SOHCAHTOA, so it's 100 sine 15. 100 times sine 15, what does that give us? 25.9 newtons. So there we go. I've now broken my F1, first vector, F1, into x and y components. Now I need to do the same for F2. There's another vector here, F2, so he needs a F2x and he needs a F2y. So let me redraw this. What do we have? F2 looks like that. He's got a force of 150. Here's my y side. Here's my x side. And what do I know? The angle that F2 makes with the vertical is 10 degrees. All right. So we do the same thing. I want the x side. I look at my triangle. The x side is the side which is opposite to my angle, so that means sine. So we have 150 sine 10 degrees. 150 times the sine of 10 gives us 26.0 newtons. Y, I need the y component. Well, the y side is the side adjacent. Adjacent goes with cosine, so 150 cosine 10. 150 times cosine of 10 is 147.7 newtons. All right. Now, first of all, if you happen to get different numbers here, just make sure your calculator is in degree mode, of course. We're using degrees for this course. I'm done. I'm done for the first step. All of the vectors in my problem have been broken up into components, in this case, x and y components. Step 2 says, to get the resultant x component, add up each individual x component. So F1x, 96.6, F2x, 26.0. So this gives us 122.6 newtons. Next, y. The resultant y, the total y component, is the sum of all the individual y components. So that's 25.9 plus 147.7. That gives us 173.6 newtons. All right, so we're almost done. What do I know? I know the final total vector, the total resultant net force, has an x component of 122 and a y component of 173. But I don't want that. What I want is the magnitude and the direction. So the last step is to calculate the magnitude of this resultant, which is the square root of the x component squared plus the y component squared. So I take these numbers, 122.6 squared plus 173.6 squared. Then I take the square root of that number, and I get 212.5 newtons. So there's my magnitude. What about direction? Theta is inverse tangent of the y piece over the x piece. All right. So calculator, 173.6 divided by 122.6. Then I take the inverse tangent of whatever that number is, and that tells me 54.6 0.8 degrees. Now, before I box the direction, if you remember, every time we do one of these problems in physics, there's a chance that our angle could be wrong. So in order to make sure this is the right angle, we have to look to see if it makes sense. How do we see if it makes sense? Well, we look to the components and we say, what do the components say this should look like? Well, the x piece is positive 122, so it's something that points to the right. The y piece is positive 173, so it's also something that points up. So I know whatever this vector is, it points up and to the right. So that means it's somewhere in the first quadrant. My angle, is my angle in the first quadrant? Yeah, it's 55. All right, because they're both in the same quadrant, I know this is the right answer. So I could box it. If, however, they didn't match, so say the components were positive x and negative y, that would imply it's something that points down and to the right. Down and to the right would be a negative or a fourth quadrant angle. I look at my angle and it's a first quadrant angle. Because they don't match, I know all I'd have to do is add up 180 degrees. Okay, so those are your two options. Either they match, and in which case, good, you just box the answer. Or they don't match. If they don't match, you just add 180, and now you're good. In this case, however, they match, so I didn't have to do anything. And now I have my answer. Here's the magnitude, 212. Here's the angle, 55. What does it mean, though? If we want to think about this, since we're doing engineering here, we want to think about this as a intuitive system. What this means is, what I can do is I could take this little hook screw thing. Okay. So there it is, a little hook thing screwed into the ground. And instead of having these two ropes being pulled on with two different forces, I could use one rope, so let's say this red rope, and say if the rope is angled at 54.8 degrees, okay, so here's my horizontal, that's my little horizontal line, so 54, that's something like this. So if I pull with 54.8 degrees with a force of 212.5, then this hook would feel exactly the same thing as the original hook did. It would not know the difference. That's basically what we did. We took a complicated system with multiple forces, replaced it with a more simple system with only one force, but what this one force does is the same as the original system's two forces. And the good thing about this is, as we progress through the course, we may have bridges, for instance, and the bridges, or let's say even, let's say a bridge. And on this bridge, there's a whole bunch of different things acting on the bridge. So a bunch of different cars are driving along. People are standing on it. Maybe there's tension wires trying to hold it up. All sorts of different forces. And you may be asked to analyze this bridge to say, okay, well, what happens if I do this? Or what happens if I double the traffic? What happens if a boat runs into one of the pilings, or all sorts of different things. If you don't know how to do this kind of a thing, then what's going to happen is every time you have to analyze the bridge, you have to go through the whole process of adding all of the different vectors together every single time. However, if you could do something like this, then all you have to do is analyze the bridge one time and turn all of the complication, all of the different cars and people and tensions and everything acting on a bridge into one single force. And then you now have the little bitty individual system of a single force that you can analyze and do stuff to. So it's a very, very useful technique to take a very complicated system, analyze it one time, create a simple system out of it, and then you can do whatever you want to do to the simple system. And it turns out, by analyzing the simple system, you get the exact same answer as if you were analyzing the more complicated one. So this is critical for an engineer to be able to do, or else you're going to be wasting your time all the time by having to look back at a very complicated system over and over and over again. But anyway, here we go. This is, at the end of the day, the component method. Nothing new. You saw this probably in your third or fourth week of General Physics 1. Adding vectors together. We have a set of vectors. In this case, they're called tensions or forces acting on the system. We want to add them together to get a total force. What you do, for every vector in your system, break it up into x and y components, and then you just list them. That way they're there for you to use. Once you have all of them broken down, then you can add the components. So you add all the x's together to get a total result in x, and add all the y's together to get a total result in y. Once you have those two things, then all you do is the magnitude and direction. Magnitude is like the Pythagorean theorem thing, and the direction is the inverse tangent. The only key is for the direction, before you box your answer, just check to see if your answer matches what the components show. So if the components are positive x and positive y, it's up and to the right, then obviously your angle must be something up and to the right. If it's not, add 180 degrees to your angle, and that's your answer. All right, so I hope this is helpful. Obviously, this is more of a review, but the next video, I'm going to show how an engineer may solve this problem with a slightly different method, still using trigonometry, but instead of right triangles, they'll have some general triangle, and thus we'll use law of sines and law of cosines to solve it. And like I said, either you like that way or you don't. It doesn't matter. We'll see how it works, and we'll see that we get a very, very similar answer. So, until next time.